Thanks. Good morning, everyone. Thanks for coming out early. I want to talk to you today about BoLD, which is a new permissionless optimistic validation protocol that is coming soon to an Arbitrum chain near you. BoLD has, I'll go into the details later, but BoLD provides a combination of features that no other optimistic validation protocol can match. I talked yesterday at BAS about the interaction between optimistic and ZK proving. And I talked then, I'm not going to reiterate that talk obviously, but I talked then about how, in my view, the best way to incorporate ZK proving into a chain like Arbitrum is via a hybrid protocol that has both ZK and optimistic components to it. And BoLD could be the optimistic component of such a protocol. So I'll try to give you an intuition for how BoLD works. I won't have time or space to go into all the details, but we have a very lengthy and detailed paper available on our website that has all of the specifics, details of the protocol, along with theorems and proofs. Okay, just to set the stage, let me talk about how Arbitrum as a state-of-the-art L2 rollup chain works, just so to give an idea of how proving fits into the overall picture. Now, basically, you can view the protocol as coming in these four separate pieces, which are independent sub-protocols that plug together to make the main protocol and interact asynchronously with each other in general. And there are four pieces. The first piece is sequencing. Its job, and its only job, is to put transactions in order. That is, to receive incoming transactions from users and to produce an ordered list of the transactions that arrived in the order that they are to be included in the execution of the chain. And I emphasize the sequencer is not trusted for any purpose other than that. Now, once we have an ordered list of transactions that the chain is supposed to execute, that ordered list is used for two things. First, for execution. Execution takes that list of transactions and uses it to build a sequence of blocks by executing a state transition function, which is deterministic. So once you know the sequence of transactions, you can then compute the one and only sequence of blocks that will follow from that, which everyone can do independently. The other thing that happens with the transactions that are produced in this sequence is they go to a data management component. And the job of the data management component is to record that sequence of transactions to some data availability source, such as L1 Ethereum. And that component does a bunch of sophisticated things involving batching and compression and so on to reduce cost. But fundamentally, its job is to record the transaction sequence to L1. And then the last piece is proving. And what its job is to prove to the L1 chain what is the correct sequence of blocks that follows from executing the sequence of transactions that were recorded by the data management system. Now, I emphasize that as soon as the sequencer, as soon as the data management system has recorded the transactions on L1, the transactions are final. Everyone knows their result, and there is a single result, and everyone knows what it is. So the job of proving is simply to convince the L1 chain which checkpoint of the L2 chain it should record. And that's the component I'm talking about today, is the proving component. Okay, so let me talk now to set some background about how rollup protocols, optimistic rollup protocols like this work, by talking about the currently deployed Arbitrum protocol. And the key data structure in that protocol is what we call an assertion. An assertion is a claim that somebody is making about which block is correct at some block height in the L2 chain. So you see in each of these boxes is an assertion, and you see that each assertion contains an L2 block height and contains a claimed L2 block hash. That is the claimed to be correct block hash at that height. Each of these assertions points to a predecessor assertion, and an assertion is claiming not only that the block hash that it contains is correct, but also that its predecessor assertion is correct, and transitively, therefore, that an entire sequence of predecessors back to Genesis is correct. So each assertion is claiming a prefix of what it claims will be the final canonical history of the chain. Now, each assertion as the protocol executes is in one of three states. It might be confirmed, shown here in green, meaning that the protocol has definitively decided that that assertion is consistent with the canonical history. Or it could be rejected, shown here in red, meaning that that assertion will never be confirmed. Or it could be yellow, pending, meaning that the protocol has not yet decided. Okay, now as this executes, there's the other piece of this protocol is staking, right? And so the rules of staking are this, that any validator can stake on any pending assertion. And when you do that, you're implicitly staking on all of the pending ancestors as well. So you can stake on an entire history with just one stake at the leaf end of that history. You can move your stake to any successor of the place you're already staked, because that doesn't unstake you from anything. And you can recover your stake if the assertion you're staked on is confirmed. Now, every pending leaf, it's easy to show that every pending leaf will have at least one stake because the party who introduced that leaf is required to stake on it. If your stake is challenged and you lose, then your stake will be slashed, you'll lose it, and that's your incentive not to stake dishonestly. Okay, now when this protocol executes, the common case is going to look like this. So here we have Alice over on the right, who is staked on a leaf assertion. And we have this long chain of yellow assertions that Alice has, all of which Alice is endorsing, which represents a single history that Alice is staked on. And over on the left, we have a prefix, which is green, meaning it's already been confirmed. And so as the chain executes, roughly once per hour, say, Alice will append a new yellow assertion on the end of this and stake on it. And also roughly once per hour, one of these yellow assertions on the left end is going to turn green because it has been proposed for long enough and no one has disputed it. And so first, if an assertion is posted and no one disagrees with it, no one posts a conflicting assertion within a time limit, then it can be accepted immediately. The other case that can come up, though, is a challenge. And this is where you have a situation like this, where Alice and Bob have staked on different histories. Now, of course, given that they have done this, there is some point at which their histories fork. And so we'll set up a dispute to decide which one of them is correct. And you can think of the dispute protocol as a kind of fork choice rule, that among the claims, competing claims made by Alice and Bob, decides which one is correct, prunes off the other one, and therefore the surviving one is able to be confirmed. So all of this is common practice in optimistic protocols so far. But the part I want to talk to you about, and the thing that BoLD solves, is how do you handle disputes like this, and not only two-way disputes, but n-way disputes, and not only one dispute at a time happening, but a possibly forking chain with multiple simultaneous disputes. How does all that get handled? Now, the current challenge protocol that's implemented in Arbitrum provides these properties. First, trustless safety, that if there's one honest validator, no bad assertion, no false assertion will be confirmed. Second is trustless liveness. If there's one honest validator, a good assertion will be confirmed. Some assertion will be confirmed, and by safety, it will be a good or valid one. Third, if the validators follow their incentives, then the protocol will execute efficiently with minimum time to confirmation. Note that correctness does not depend on any incentive argument. Incentives only affect the efficiency of the protocol. A bad actor can only make the protocol less efficient, and that's actually fine because if they do stake incorrectly, we're going to take a stake from them, and so we'll make the bad actor pay for the cost of the dispute. A malicious validator can cause delays, and in the current Arbitrum protocol, the worst case delay attack allows an attacker to delay confirmation by n challenge periods if they're willing to sacrifice n stakes. And that's not a great situation to be in. And this is why in the currently deployed Arbitrum 1 chain, validation is permissioned. So what BoLD gives us is a way to eliminate this last problem and get from worst case n challenge period delay to worst case constant delay. And I'll explain how that works. But first, I want to talk a little bit about L1 censorship and the challenge period. In an optimistic protocol, basically any L2 protocol in general is going to rely on the ability to post transactions on L1 Ethereum. But Ethereum is subject to censorship attacks, and an adversary who controls a third or more of the Ethereum stake is able to sustain a censorship attack essentially forever. But there's a current social consensus in the Ethereum community that any censorship attack longer than 7 days would be met with a social response, a social hard fork in Ethereum, essentially to, by social consensus, confiscate the stake of the attacker and allow the chain to move forward. So how do we take this and turn it into an actual threat model we can use to design and analyze a protocol? Here's how we do that. We formalize this as a threat model like this. We say, first of all, that the adversary is able to censor any Ethereum block or blocks of its choice. But it can't censor more than some maximum number C of blocks during an execution of the protocol. So think of C as being that 1 week assumption, max assumption. The adversary controls the contents of every block, but they're required to include any transaction that's submitted within at least some number delta of non-censored blocks. So they can keep your transaction out for as long as they like if they're willing to produce censored blocks. They have a limited budget of those. But in the absence of censorship, every transaction has to be included within delta blocks. That's the formal threat model and how we model the worst case behavior of Ethereum censorship. Okay, now let me switch gears and talk about the BoLD protocol with that established. First of all, let me talk about some things that change in the kind of design logic of the protocol. Whereas the old protocol functioned as a 1v1 challenge, that is, there were two parties who were contesting, and one of them would get identified as a liar and then ejected, and their stake confiscated. In the BoLD protocol, it's an all versus all challenge. If there are n competing stakes, then there is a single protocol that picks one winner. As opposed to picking one loser out of two, you pick one winner out of n. In the old protocol, the contestants are stakers. So if you're an honest party and you stake, then you're a contestant in the protocol. Whereas in the BoLD protocol, a contestant is one of the branches in that assertion tree. And so if multiple people are willing to stake on the same branch, only one of them actually needs to stake. And everyone who agrees with that branch can fight challenges as a team. In the old protocol, you identify one staker to slash and remove, and in BoLD, you identify a winning branch. And I'll show you by way of example how this works in a little bit. So in the old protocol, every party, each honest party, needs to stake separately. If you are an honest party and you're not sure that whether the parties who are staked correctly already are honest, you would need to stake yourself and you would need to fight separately in challenges. Whereas in the new protocol in BoLD, you only need one party to stake honestly, and then all the honest parties will fight as a single decentralized team. The adversary in the old protocol can cause n weeks of delay by sacrificing n stakes. In the BoLD protocol, the adversary can cause one challenge period of extra delay, and that only by censoring. And then the other advantage of BoLD is reduced total cost. In the old protocol, the honest party's total cost is proportional to the number of honest parties. And here, it's proportional to the number of stakes that are slashed. And what follows from that is that you can reimburse the costs of the honest parties from the slashed funds in all cases. Okay, let me talk about how this actually works. And I can't advance the slide for some reason. Sorry. Yeah, perfect. Okay. So let me give you an example of a dispute in BoLD. So over at the left, we have and we'll assume that over at the left, we have an agreed upon starting point where all the three parties, Alice, Bob, and Charlie, who are in this dispute, all agree on a state at height 0. And now each party, Alice up at the top, has asserted something at block height 2048. And now instead of just asserting what is the state at block height 2048, she instead is going to commit to a vector of all of those 2048 states. And she's going to commit to them by publishing a Merkle root of the Merkle tree formed from those 2048 leaves. And Bob similarly, and Charlie have staked on different Merkle commitments to the entire history of the chain from block 0, where they agree, up through block 2048. So we start in this situation. Okay, then let's suppose that Alice is an honest party. She wants to advance the state of the protocol. So what Alice is going to do is she's going to bisect that top edge. Next slide, please. Thanks. And so she's going to produce a new assertion at the midpoint. That's at height 1024 with some Merkle root. And she has to prove that that Merkle root is consistent with the Merkle root that she bisected from. In other words, that her Merkle root at height 1024 is committing to a prefix of the vector that her leaf Merkle root was committing to. And that's a very simple just an unwrapping of one level of the Merkle tree. So Alice does this. And the other notion that is built into this protocol is the notion of a presumptive edge. When Alice does this, each of the two edges, next slide, please, that came, thank you. Each of the two edges that were created are now labeled as presumptive, which I'll draw in red. And what that means is that they have no rival that is the same length or shorter than them. And so they are, in a sense, in the winning position. They're in the lead in the contest to be confirmed, conceptually. And so those two edges are now presumptive. Okay, now let's suppose that Bob, who believes in this middle right assertion, is going to bisect his assertion as well. He wants to respond because now Alice's edges are presumptive, and they are, as I'll explain later, making progress toward winning the challenge. Bob needs to respond. If he doesn't, those presumptive edges will be confirmed and Bob will lose. So Bob is going to bisect. Bob constructs his halfway point edge. He needs to, again, prove that it's Merkle consistent with his endpoint. And in this example, it happens to be equal to the midpoint edge that the midpoint claim that Alice made. And so we now have this situation, right? So notice that Alice and Bob, when they bisected, agreed on the first half of the bisected execution, but disagreed on the second half. Notice also that up on the upper right, the edge that was previously red, presumptive, is no longer presumptive because now it has a rival of the same length. The one over at the left is still presumptive. Okay, now the protocol can go forward from here. Let's say that Charlie now bisects his edge down here. He disagrees with the halfway point of Alice and Bob. And now the upper left edge is no longer presumptive because it has the same length rival. But this edge on the lower right is presumptive. And you'll note that this edge will forever be presumptive unless someone comes in with the fourth claim. This is going to stay presumptive forever. The story can go on. Charlie can bisect his lower left edge here like this, creating two new presumptive edges. Now, either Alice or Bob might respond by bisecting the upper left edge, leading us to a situation like this, and so on. So you can see how this protocol makes progress by basically refining this tree by bisection. But unlike previous protocols, the fact that parties can agree on midpoints allows you to reduce in the general case, to reduce how many nodes are in this graph, and therefore to reduce the complexity of the protocol in important ways. One other thing to note is that although I have drawn in this diagram the bisection as replacing a long edge by two half-length edges, in the actual protocol, the long edge still exists and it has bisection children, which are the two shorter edges. But if I put that on the graph, it would be unintelligible. But just bear in mind that there is, in addition to this sort of path-based representation, you can imagine as well that there's a kind of bisection tree, actually bisection DAG representation here. Bisection DAG because when parties bisect different edges, they might agree on the left half. So, and that's sort of what's happening here. Okay, so this process is going to go on. Parties are going to continue to bisect the edges. They're motivated by the fact that that they would like to win the challenge by making their own edges red and presumptive. And the honest party will do that in order to try to win. The dishonest party will have to also bisect in order to keep the honest party from winning by default. Okay. Eventually, when you bisect, you'll reach a situation like this, where you have a one-step fork, where at height 678, you have agreement between some set of parties, but at the next height, 679, they disagree. So now there's a single execution of a single block where the parties disagree. That's a one-block fork, and you're going to respond to that with a one-step proof. You're going to do a simple proof just of the execution of that block to identify, in this case, that the bottom path is the one that's correct by directly proving it, thereby turning that lower edge red and presumptive, which is its permanent state. And so now you know that at least if the path to the left of this 678 is actually valid all the way back to the root, that the correct execution will follow the red path through here, or at least that's the presumption at this stage in the protocol. Okay, now I talked about how you have these presumptive edges, they have an advantage, they're working toward winning. Let me tell you what that really means. What that really means is that the protocol has a notion of timers on edges. Each edge has an edge timer which measures for how long it has been presumptive. So if it becomes presumptive, that timer starts ticking upward. At some point, it may stop being presumptive, then that timer stops. And once it stops, it can never start again. So each edge has its local edge timer. We also have a bottom-up aggregate timer. That is the edge timer, the aggregate timer of an edge is equal to its local edge timer plus the min of the aggregate timer over its bisection children. I apologize for that error. It's plus the min of the aggregate timer over the edge's bisection children, or it's infinite if the edge has been one step proven. And now we say that we can confirm a top-level edge if its bottom-up timer is at least C, that max number of censorship steps, plus a lower order term that you can see in our paper. Right, so this is how a challenge ends. Some top-level edge, if it's accumulated enough bottom-up timer, intuitively, if it's spent enough time in the lead in the bisection protocol, if all of its steps have spent enough time in the lead, then it can be confirmed as correct. And although it's probably far from obvious, and in fact it is far from obvious that this protocol is sound, our paper proves that it is. Okay. So, in order to prove that, the first thing we need to do is define an honest strategy, right? The theorem is going to say something like, if any party is following the honest strategy, then something follows. And the honest strategy is just this. First, if nobody has made an honest top-level assertion, make one. Second, if some top-level edge can be confirmed to end the challenge, confirm it and end the challenge. And third, if there is some honest edge in this bisection graph which is not presumptive, then do something to defend it. That means if it can be one-step proven, then one-step prove it. Otherwise, bisect it. This is the whole honest strategy. This is all an honest party needs to do. And then we have two theorems that have detailed proofs in the paper. First, the safety theorem, that if any one party is following the honest strategy, then no dishonest top-level edge can be confirmed. And then second, the completion theorem, which is not only liveness, but also a bound on completion time. That if anyone follows the honest strategy, the protocol will complete. And according to the safety theorem, it can only complete by confirming an honest top-level edge within a time which is 2C plus a lower order term. Okay. There's one more piece I need to talk about with respect to security of this protocol, and that is economic security. Economic security, in particular, talks about an adversary who wants to do a delay attack. That is, the adversary is willing to sacrifice one or more stakes in order to delay the confirmation of some particular assertion. Notice that the adversary can't affect the finality of the assertion, only its confirmation onto this, or settlement onto the parent chain. Okay, now, economic security essentially requires that we need to impose at least some minimum threshold cost on the adversary in all delay scenarios. That is, anything the adversary does, any strategy they can follow that leads to delay must cost them at least that threshold cost. So that has a couple of implications. First of all, that it's a mistake to design the protocol to give the loser's stake to the winner. And the reason for that is that if you do this, then the adversary can stage a self-challenge where one Sybil stakes dishonestly, another Sybil stakes honestly. The honest Sybil defeats the dishonest Sybil, and the adversary pays themselves a stake. That's a zero-cost delay attack. And there are deployed protocols today that suffer from this. But this protocol doesn't. And then the other implication is that this implies that at least one honest staker has to stake at least that threshold amount, right? Because the protocol doesn't know which staker is honest or dishonest. If two people are staked, they both have to stake that amount because either one might turn out to be dishonest. And so this implies that some honest party needs to stake this threshold amount. And that, again, seems to be a requirement that seems to be a necessary condition for economic security. And indeed, BoLD does do that. Okay, now, the actual protocol, in order to be deployable, has this sort of an annoying generalization, which I have saved you from so far because it makes the protocol somewhat more complicated. Our paper deals with this in full detail, including a proof of the general case. And that is that in practice, if you're going to prove a large amount of computation, say an hour of computation, on a very high throughput chain, like Arbitrum 1, you might need about 56 levels of bisection. And that means that in order to compute your Merkle tree, you need to compute 2 to the 56 hashes. But in fact, each of those hashes is a state root, which itself requires some hashing to compute. And you can't really afford to do this on an ordinary node in the time you have. And so instead, you want to do multi-level BoLD protocol. First, you bisect over the blocks in the assertion to reduce the dispute down to a single block. And then you recursively use BoLD again to resolve that dispute by bisecting over the instructions of execution that generated that block. And in fact, in the protocol that's currently deployed on testnet, there's actually 3 levels rather than 2, because in the execution step, in the execution layer, you would have 2 to the 42 state roots, which is still too many. So multi-level BoLD says you're going to bisect over some, say, larger step of computation instead of every individual step. You're going to have some stride of 2 to the k steps, and you're going to build a vector of the states after 2 to the k, 2 times 2 to the k, 3 times 2 to the k, et cetera, steps. You're going to run BoLD over that until you've narrowed the dispute to a dispute over 2 to the k steps. Then you use BoLD recursively. You need to do a bunch of subtle stuff at the point of recursion, and again, our paper goes into all the details. But this is something that you need to do, which makes the explanation somewhat more complicated. Okay, so let me summarize all of this by talking about the guarantees that BoLD provides. First, if any party is following the honest strategy, then no false assertion can be confirmed. Second, if any party is following the honest strategy, then some, because of safety, true assertion will be confirmed within time 2c, 2 times the censorship limit, plus a lower order term. And that clock starts at the time that the first of the rival assertions was posted. So if Honest Alice posts an assertion right away, the clock starts on that 2c plus lower order term right then, even if the adversary joins the challenge late. And then third, economic security. If there is a challenge, malicious posters lose at least 1 stake in total. So BoLD is, to our knowledge, the only protocol that provides all of these guarantees. And so we think it is an excellent protocol to use for optimistic dispute resolution. So let me talk about the status of BoLD. The code for BoLD, the paper and a security audit have been released. The paper on BoLD will appear at AFT. That a BoLD testnet has been live since April 15th. And so there's been a fair amount of activity sort of beating on it and trying different challenge scenarios. And the BoLD implementation is heading toward a vote of the Arbitrum DAO for adoption on Arbitrum 1 and Nova, and will be available on any other Arbitrum app chains actually technically available today. And that's it. Do I have time for questions? Great, thanks. And while I take questions, let me just thank my teammates. 10 teammates listed here, and the ones that are underlined are at SBC. So if you see any of them, feel free to pepper them with questions as well as me. Okay, any questions?
Hi, thank you for the presentation. I'm trying to understand better about how the sensor time factor into the total time taken, since I'm understanding that the validity proof helps reduce the amount of time necessary, and also the fraud proof kind of potentially increase the time needed to find that consensus. So if, let's say, the censorship's only taking, like, let's say max 1 day, how would you elaborate what's the additional time needed for these lower order terms?
Yeah, so the lower order term is a constant, and let me tell you basically what it is. The lower order term, and I might get the constant slightly wrong, is 3 times that delta parameter, which is how long it takes to put a transaction on chain in the non-censored case, times the max number of levels of bisection. So it basically, so you can think of it as roughly speaking, the time it takes for a back and forth game to be played out all through all the bisection levels, assuming that both parties are moving immediately and there's no bisection. So that's like the minimum time it could take to resolve a dispute if there are 2 parties and they're going as fast as they can and there's no censorship, multiplied by 3 halves. And the 3 halves is a technical factor you need to make the proof work.
Got it. Is there any term for the validity proof side? So the part for the one-step proof?
That is part of that lower order term. That takes time delta.
Hi, thanks for your presentation. I would like to ask some further explanation on the connection of the various BoLD levels. Specifically, how do you prove that the lower recursive BoLD level is properly connected with the previous ones?
Yeah, so in the lower level, a party will make a top-level assertion within that lower-level BoLD protocol, and they have to prove that, so let me make this concrete to simplify the explanation. Suppose that the top-level bisection is over blocks, and the bottom level and the recursive one is over the instructions to create that block, right? So that bottom-level assertion will include, as part of it, the output of the block building function. And so that needs to be consistent with one of the branches of the one-step fork at the higher level. So you have to prove that basically the block building output that you are claiming at the lower level matches one of the branches at the upper level. And that association between that lower level assertion and the upper level one-step branch is maintained by the protocol. So and there's a rule for propagating bottom-up timers from, there's a rule for propagating bottom-up timers across those level boundaries, which is described in the paper and proven sound in the paper.
Thank you.
I'd be happy to answer more questions out in the hall later. Thanks.